Thank you for the introduction. Yeah. So in interactive virtual environments, effective sound can contribute to a user's sense of presence in the environment. Ideally, this sound should be responsive to the user and their interactions in the environment. And by using physically based methods, the sound can dynamically react to the specific details of the interactions being performed. In this work, we specifically look at impact sounds produced when rigid objects are struck. These sounds are common in everyday environments. Let me make sure audio volume's up. Yeah. And there are a few methods for simulating these sounds, including digital waveguide synthesis and modal sound synthesis. So here's a demo showing some impact sounds within a virtual environment. These are sounds produced using our method. In order to synthesize realistic impact sounds, we need real-world material parameters. These include the material's Young's modulus, density, Poisson's ratio, and a set of damping parameters. By varying these parameters, we can create the sounds of different materials. In this work, we focus on the damping parameters, which characterize how vibrations decay over time and are more difficult to accurately model. This brings us to the question of how we can pick the correct material parameters for a given virtual object. For someone designing virtual objects, it would be convenient to automatically reproduce the material parameters of a real-world object. We call this audio material virtualization. And furthermore, since these material parameters have been shown to be geometry invariant, if we can take a real-world object and figure out its material parameters, we can then transfer those material parameters to any other virtual object. There has been prior work on automatic parameter estimation using recorded impact sounds as input. However, this prior work requires additional knowledge about the object, including the object's geometry, the exact point at which it was struck to create the impact sound, and the object's Poisson's ratio. Additionally, there may be some external factors which influence the observed damping rates, which have required the sounds to be recorded in carefully controlled environments. The factors affecting damping include material damping, which we want to model, as well as support damping, in which the way an object is held affects the sound it produces. Here's a quick demonstration of that. There are also a number of acoustic effects which can affect the observed damping rates. And so we present the first probabilistic model for estimation of material damping parameters while taking into consideration these external factors which can affect damping. Our method does not require knowledge of the object's geometry, the hit point, or the Poisson's ratio. We perform our evaluation by establishing and comparing against a human baseline as well as through a perceptual study. For modal impact sounds produced by rigid objects, each frequency damps at its own rate. So given a set of impact sounds that have been recorded, we can construct a data set of frequency damping features. And you can see in this plot some of these features where the frequency is approximately the eigenvalue is approximately the frequency squared. And you can see that for any given eigenvalue, there is a distribution of possible damping values which can be observed. And so we propose to use a generative model of the probability distribution of these damping values. We start by modeling the probability of observing a certain rate of damping given the eigenvalue and a set of model parameters. We model some external damping factors using a normal distribution. This is centered on the material damping with its own standard deviation. And for some external factors, we use an exponential distribution for the modeling. The result is an exponentially modified Gaussian distribution, which models the combined effects of all these various sources of damping. So we can take a number of sounds and extract these frequency damping features, and then we perform maximum likelihood estimation to optimize the distribution parameters to maximize the likelihood of the observed damping values. As a result of this, the optimization process produces the optimized material damping parameters, which can then be transferred to a virtual object to produce realistic sound. Here are some examples of parameters estimated using our method for two different damping models, the traditional Rayleigh damping model and our extended hybrid damping model. In this table, in general, larger values imply a higher rate of damping, which means the sound decays faster. So we would expect that between a steel wrench and a plastic bowl, the plastic bowl should have larger values. And we can see that is the case with our estimated parameters. And we can observe a similar pattern among our hybrid damping parameters. For validation, we performed two user studies, the first being a human hand-tuning study in which we had human subjects perform the same parameter estimation task that our automated method performs. And this was used to establish a human baseline for comparison. We also performed a perceptual evaluation study in which subjects evaluated their perception of material of various impact sounds in order to compare a recorded reference dataset to datasets of synthetic sounds. So starting with the human hand-tuning study, here we had a number of subjects. Each were given some real-world objects which they could strike to produce impact sounds. They also had a user interface through which they could produce sounds for a virtual version of the same object. These two sliders, A and B, controlled the material damping parameters for that object. So by sliding them around, the damping values would change. And the subject's task was to identify the slider settings such that the synthesized sounds most closely matched the real-world sounds. And so we had 20 subjects who tuned the two Rayleigh damping parameters, and we had an additional 20 subjects also tune the specific modulus of the material. For most materials and parameters, the subjects were able to agree on what the ground truth value should be for that parameter. There were a few cases, particularly for alpha 1 for heavily damped materials such as wood, where there was more variance, but in most cases there was high agreement. For the two-parameter version of the study, the subjects required a median of 145 seconds to perform their optimization and 28 synthesized sounds. In addition to this, the human hand-tuning method requires that a precise 3D object geometry be provided, which may take several minutes to several hours to construct, depending on the object. In comparison, our method is automatic, given the recorded audio, and significantly reduces the amount of human effort needed to perform this estimation. Moving on to our perceptual evaluation study, here we had subjects answer questions about 40 individual impact sounds. For each impact sound, or for each object, there were 4 data sets. There was a recorded data set of a reference sound. There were sounds synthesized using parameters from previous work, REN. We had a data set of sound synthesized using our hand-tuned parameters, and a data set of sound synthesized using our automatic method, EMG. For each sound, the subjects were asked to identify the shape and material of the object that produced that sound. And they are also asked to rate these 4 descriptive qualities about the object on ordinal scales. These are material confusion matrices for each of the 4 data sets. An ideal synthetic data set would not necessarily show a perfect diagonal line, but would instead replicate the same pattern of errors that is seen in the reference recorded data set. Of the 3 synthetic data sets, the hand-tuned data set is most similar to recorded, validating our hand-tuned parameters. Our automatically estimated EMG results are also similar, but require significantly less human effort to obtain. We can also look at the descriptive qualities obtained from the subjects. Again, here, an ideal synthetic data set should replicate the qualities of the recorded data set. So in this chart, we can see the average error of each of the 3 synthetic data sets as compared to the recorded data set, where lower is better. Our hand-tuning results are effective at reproducing the qualities, particularly duration and ringiness. In comparison, our method, EMG, produces perceptually similar results in pitch and tonality, while having lower error than REN, the previous work, on all qualities except for tonality. And so we can now look at some demonstrations of our results. All sounds in these videos are synthesized in real time using material parameters estimated from real-world objects. And here are some wind chimes of various materials. And so to conclude, our probabilistic damping model enables robust audio material virtualization. Our method does not require any knowledge of the object's geometry or the hit point that was used to produce the sounds. And the sounds can be recorded in less controlled environments as we account for the various damping factors. Our human hand tuning study provides a baseline for comparison for automated methods, both ours and any future methods, while our perceptual evaluation study validates both our hand-tuned and our automatically estimated parameters. A few limitations of our work are that we assume that our damping features are independent and identically distributed, which may not hold up in practice. And while our method can work with a small number of input sounds, we found that optimal results were achieved with about 20, which may still require some time and effort to acquire. For future work, we would like to look at applying probabilistic modeling to estimation of other physical parameters. We would also like to explore the challenges of object virtualization for augmented reality applications. I'd like to acknowledge our funding sources, and thank you. So in this case, tonality is mostly, we saw it on a scale from being a pure tone to a mixed tone, where a pure tone would be more like a musical instrument, and low tonality would be more like a drum strike, something that's a large number of different tones. I don't believe that there was a statistically significant difference between these three. But for hand tuning, why might there be higher tonality? So part of it might be that for when humans are hand tuning these material parameters, at least when I hand tune the material parameters, I tend to try to identify a specific pitch within the real object and a specific pitch within the synthesized object. And I try to align those two. So if the other subjects were trying to do that same thing, they may be specifically looking at the tonal parts of the sound, trying to align those, and getting thrown off by that.